So this is problem A, number 15. And in problem A, number 15, we have a coffee pot that has a heating element with a resistance of 49.5 ohms. And it says the coffee pot is on for 30 minutes. So that's clearly a time. And we want to know how much heat is released. So we're looking for Q to begin with. Then it says if it contains 3 liters of water, how much of a temperature change was there? So we're also looking for delta T. Now, the problem is when we have power and time and all that kind of stuff, time has to be in seconds because, again, watts are joules per second. So we want this to be in seconds. So what do we have to do to change that to seconds?
Multiply times 3,000.
So, no, multiply it's in minutes, so it's just times 60. So 3 times 6 is 18. Each of them have a 0, so that's 1,800 seconds. Then we have that 3 liters. What is 3 liters? Well, that's a volume. But the problem is water has a density of 1 gram per milliliter or 1 kilogram per liter, which means this is really also equal to 3 kilograms of water, so that gives us an M. So that's a handy dandy thing to know about water, is the volume and the mass are always going to be the same. If one's in milliliters, then it's in grams. If it's in liters, it's in kilograms, but they're equivalent. So we need to find Q and we need to find T. Now the first thing we have is R and we have T and we have the fact that the coffee pot is plugged in where? Say to the wall. It's plugged into the wall. What's the voltage?
120.
120.
So we know these things, and from these things we should be able to find Q. And again, Q is, in this case, the work that we do with the coffee pot. The whole point of the coffee pot, plugging it in, is to make it warm. So the work that we're doing is generating heat. So again, if power is equal to work over time, and the work is really the heat, then I just need to bring the T up. And I say, hey, Q is going to be T times power. But I don't have power, I have V and I have R. So instead of P, I'm going to put in IV because I know P is equal to IV, and the T is in there also. So I have IV, but I have V and I have R. So I want to get rid of I and replace it with, yeah, again, I know V equals IR. So if I want to get rid of I have to say, hey, that's equal to V over R, so that means it's V squared. Everybody catch all the tricky algebra there? Yes. Alright, so we know all that stuff. So we say, hey, that's 120 squared times 1,800 divided by an R of 49.5. How many of you, when you plug into a calculator, say that in your head? Just serious. I'm curious if it rubs off on other people. You hear the square in your head even if you don't say it. Sometimes. I'm just seeing how much of a influence I have on you guys. So Q here is going to equal 5.236. I was going to put it into. Okay. Anyway. Yeah. I didn't exponent it after all.
Yeah, because I got that. And then I saw that.
So we got that much. And most of you got that far and you didn't have too much trouble. What you didn't have is the second part, delta T, and you're saying, how do I find delta T if I have Q? And ideally you remembered from last year that you say, oh yeah, Q is equal to MC delta T. So I already know the Q. And to find the delta T, I just need to divide by MC. So then I say to myself, well, hey, I know my M was 3. So I'm going to divide that by 3. I also need to divide it by the C of water. And ideally, you guys remember from last year, since we use that number so often. That number doesn't look familiar to you?
Yes, it does. Specific.
Specific heat of water?
Yeah, like
4180?
Original was 420. 4,200.
Ice was like 2,000.
2450 was alcohol. 450 iron.
I think it was just always ice.
Ice is 2016. No, yeah, 2016. Steam is 2020.
Coca-Cola. Freddie was Coca-Cola.
Okay, so if you divide that number that's already in your calculator by 3, and then you divide it by 4180, you get, hey, it got 41.76 degrees warmer. Hey, that's what the answer says.
Whoa.
Oh yeah, long time.